Okay, so let's start. So today we have Eylem. She will talk about constructing, what is that, skin?
Stein.
Oh, yeah. Stein. Stein exotic for manifolds. Yeah, sure. It's Stein. Good. Okay, so please, Eylem.
Okay, by the way, thank you so much for the invitation, Nikita. That's great to be in St. Petersburg. So this is whatever I'm gonna tell you today. It's mostly joint work with Upload, and it's gonna be about like how we construct Stein exotic form manifolds and why we are interested in it actually. So the main interest here, let's give some motivation first. Then I'm gonna talk about a little bit in concordances in some particular tree manifold, which has a great importance in our construction. Then I'll tell you about the construction. And this construction still has like some open area that, I mean, you can really improve it. So our interest is, during that talk, is all gonna be smooth, compact for manifolds. With or without boundary. And the main tool that you'll be always using are handle bodies. So if you are not familiar with the handle bodies, they are just thickened cells. So you know what is like cell CW complexes. So you're attaching like cells and you're constructing something. And here you're just using thickened cells respect to the dimension of the space, but you're attaching in a nice way. So, and the general problem given form manifold, given a form manifold, say W4, and the problem is does it admit exotic smooth structure? That means, is there a manifold called W tilde such that W tilde is homeomorphic to your initial manifold, but not diffeomorphic? There is no such diffeomorphism usually. Okay, so when it's the case, we call that W tilde is an exotic copy of W. Then it exists. Then how many? So are there infinitely many smooth structures, for instance? And in both closed case and with boundary case, there are examples. With infinitely many.
Is it countably many, or it may be even uncountable?
I think for the compact cases, it should be countably many. There should, I don't remember exactly, but I mean for compact manifolds, if there is, I guess that should be countable. Those examples are countable many.
Yeah, because I know that there are examples with countable number of exotic structures. I know that for R4, there is uncountable.
Yeah, open cases are different than the compact cases, actually.
Mm-hmm.
So infinitely many, those are countably many smooth structures. And maybe the examples are, for the closed case, you can think about K3 surface, or sometimes it's known like Hammer surface. And the example 2 maybe with boundary case. This is the closed case, and the with boundary case. I'm not going to tell you what is that manifold, but this manifold is indeed this manifold. I'm going to call that manifold as M4 has infinite many. Those both has infinite many structures.
Can you at least briefly recall what is that? So you have some knot and you have some framing, and probably you just
yeah, this is a 4 manifold obtained by B4 attaching a unique 2 handle. Attaching 2 handle means like taken 2 cell. You can think like D2 times D2 along the partial boundary S1 cross D2, and S1 represents that knot, and D2 part, how you frame this, how you extend this diffeomorphism over over S1 to the neighborhood. This -2 represents that framing. Okay. So this is a 4 manifold obtained by E4 and attaching a unique 2 handle, which is D2 times D2, and which is attached along some partial boundary, which is boundary of D2 times D2, which is S1 times D2. So this S1 piece really is this knot that you see in that picture, and the framing part tells you how you write this diffeomorphism from S1 cross D2 to,
okay. Thank you. Yeah.
Sure. So those are 2 examples. And the second example, actually, okay, I'm going to tell more about that, but soon, very soon. So, and open problems here. The motivations of the field actually open problems. Of course, people are interested, is there exotic copies of S4, CP2, S1 times S3. Maybe I should put 2 question marks. And the last one is S2 plus S2. Okay, so those are the main interests, like the biggest open problems in the field, and we are playing around those methods. And what are the approaches? So the general approach to the problem, maybe it's the only one. Once you are given, once you are given W4, you just do some surgery operation, and you ended up with some other manifold, and hope is here. Do not change the homeomorphism type. Means you really want them to be homeomorphic to each other after that operation, but the hope is changing the diffeomorphism type. So when I say surgery, I mean, it's just a matter of terminology. You can think about many things. So can be not surgery. Oops. Can be glass twisting. Can be log transformations. Can be crop twisting. And those are really like well-studied things. And indeed, the example one uses that. And the example two use crop twisting. There are many examples here. There is an open question here.
Could you briefly recall what is Glücktwisten? Because I know about others, but Glücktwisten, I don't remember. What is that?
Yeah, Glücktwist is just doing surgery to embedded S2 if you want to keep the homeomorphism type, you are interested with homologically trivial S2. So you find an embedded S2 in your space, and you remove the tubular neighborhood of this S2, S2 cross D2 in D4, right? Then you glue it back via some non-trivial diffeomorphism of S1 cross S1. And there is a unique orientation preserving diffeomorphism of S1 cross S2, which doesn't extend in the S1 cross D2. This is literally that keeping the S1 direction as identity and like rotating the S2 once when you go
Okay, thank you.
Yeah, exactly. So, and the open question here in the non-orientable case, I think due to Akbulut, and I'm not sure about the other one, but there are examples that using relativistic to produce exotic manifolds, but in the oriented case, so far there is no known example, and we also don't know if it gives. I mean, you can like state an open question as maybe if just in case that people are here interested with the open questions. I'm not sure if there are like any students in the audience, but if you are a simply connected manifold, then is the black twist operation always gives. Oops, using the same one as before. Say you do this operation, you get W4S as gives the geomorphic manifolds. So, and our main interest here is this piece actually. We are interested with that crop twisting, and our construction relies on that. Maybe I should just shortly define that crop twisting. The definition of Koch is a pair, a form manifold, and a boundary diffeomorphism, where you want W4 to be contractible Stein, and you want that boundary diffeomorphism is an involution, such that it extends inside of the form manifold as a homeomorphism. but not as a diffeomorphism. Okay. So I think I hope the definition is clear. And coaktivisting means is really that picture. Let me find this picture. It's here. This is from Salman's book, actually, Massive Rowan Pictures. So you find that contractible piece in your manifold M. This is your whole manifold, and you find this contractible piece inside. You remove this piece, and you glue it back by this non-trivial boundary diffeomorphism. So this operation is called coaktivisting, and there is a theorem.
Excuse me. You ask W to be Stein. What do you mean by Stein?
The theorem is coming here. So here is the theorem.
The question is about Stein. What do you mean by Stein?
I'll tell you very soon. So okay, so let me state the theorem, then I'm gonna tell you what is Stein for us. So this is Salman Akbulut and Slava Matveyev. Let M prime be an exotic copy of closed, smooth, simply connected for manifold. Then M and M prime are related by coaktivisting. As a ball. And in this decomposition, actually, the both W and N piece are both Stein. And what is a Stein? So I'm gonna explain it over an example. Actually, Stein is like some geometric object, right? Say some geometric condition on the manifold. But for us, by Alishbach's like topological characterization, so we can really define in that way. We call that X4 is Stein if it has only 1 and 2 handles, such that a touching circle of 2 handles are, they are frame linked, right? In Legendrian position. Frame link in S, let's say, in connected sum of S1 times S2, some copies, depending on number of one handles, because whenever you attach a one handle, you ended up like S1 cross B3. So for each copies, you have like S1 cross S2. So the framing TB minus 1, so or smaller. Maybe we don't need that one because we can always make it. So what I'm saying here, here's the picture of what has been Stein. So that is the example of a cork, which is called a fruit cork. That's a constructible manifold. There's a really boundary diffeomorphism which doesn't extend inside as a diffeomorphism but as a homeomorphism. And the right picture is really, I mean, this piece is attaching one handle. Literally, like attaching one handle is like seeing pair of balls, because you are attaching S1 B1 cross B3 is by partial boundaries, which are like pair of balls. So you see on S3 like this pair of balls, and this is the attaching circle of your two handle. You put your attaching circle of two handle in a Legendrian position. When I say Legendrian position, by just exactly, you want this, like all the crossings look like negative crossings, and you only want to see like some cusps in the picture, nothing else. And this you can always do by even locally. If you have like positive crossing, you can just play locally. You can make it looks like negative by the price of introducing some extra cusps somewhere. So that's always possible. So you put it in this position, like your circle in here looks like that, which is the case here. Then the TB is calculated as like blackboard framing, which is really right of this knot, means that you just count this sub intersection, how many times it turns around itself. So means you're counting this that sub intersections, and minus the number of right cusps, which is here 1. And the right is here if you calculate, if you just orient your knots, and things go here, comes from here. If you orient in that way, then you have really the right backboard framing 3, and number of right cusps is just 1, and it is 2, and it has only 1 and 2 handles. It satisfies the condition. Actually, you are attaching, like here your framing is less than 2, right? Because it's supposed to be TB minus 1, which is supposed to be 1 or less. So 0 works, because you can always, like putting some extra cusps, you can make this number smaller and smaller. So this framing works. That is to say, by this characterization, that manifold is also Stein. So you have a constructible manifold, which is Stein with a like boundary evolution. Then that's the cork by definition. And does it enough? I mean, whatever you know about the Stein, that is really corresponds to that one. So normally you can talk about more geometry, but it's not necessary here.
For me, it's fine, because previously I heard only geometric definitions of Stein, and I always forget them. But topological definition.
Steins are, some complex manifold, but you want it embed holomorphically in some complex space, right? And those are like not open manifolds. Those are, when I say Stein, we are really talking about the Stein domains. It's just cut out of some piece of this Stein manifold by some Morse function, which you want this, I mean, cut it in a nice way of the boundary. So there are like some conditions on it to make this cutting nice. And that is the characterization, and which is enough for us. But that's why we care about this piece, because I stated the biggest Occam theorems in the field, right? So constructing these small exotic manifolds. But that decomposition theorem says that if there are such exotic manifolds, that should be related by some by some corks. And since in their constructions these pieces are also Stein, gives you like some rigid condition, it's good to have like some Stein exotic manifolds. Then you might be do some surgery operations to that, or you can compactify them to some close thing. So that's why we're interested. And the theorem that we have, wait, afterwards, with someone, is really, there is a pair of contractible, and we have another theorem. I'm going to state them together. In the second one, you can just change this contractible piece to homotopy S1. Stein manifolds. Let's call W1 and W2. They are exotic copies of each other. Such that of course, before that, it was known that there are such examples. There are like maybe infinite many copies of that by following these infinite order corks. But we don't know, at least it's not written. I mean, in theory, we believe there is a open problem. Maybe I should state it at the end. Let's talk about this a little bit and understand what's going on here. I mean, I'm going to state it again, but the open problem is here. Can you find infinitely many Stein copies of exactly the same manifold, of the same manifold? So there are infinitely many, it's easy to construct like infinitely many copies of pairs, maybe, which is easier, but can you make them all Stein? I mean, I think you can make this Stein too, but the problem is like, can you find the infinitely many copies of the same manifold, which are Stein?
With boundary or without boundary?
Those manifolds are with boundary by, yeah. When I say Stein domain, I mean, we're talking about manifold boundary. I mean, all this talk, everything is compact, yeah. And Stein makes it a boundary, Stein domain. So, and two corollaries here. Maybe, I mean, the LH works. If you have a Stein manifold with boundary S3, then that implies this 4 manifold must be B4. And whenever something is true, like S3 and B4, you want to ask the same question: hey, is it true for the like contractible manifold? If I change my B4 to contractible case and the sphere to homology sphere, so not true for contractible manifold and homology spheres. So, okay, being Stein is very rigid, but not that rigid.
But why do you call contractible those who are homotopy to S1? Is there any motivation?
Say again?
You say that...
oh, no, this is second theorem, actually. So I say that I'm not going to state as a second theorem. There's a pair of contractible manifold, and we also, as a second theorem, we also like homotopy S1s.
Ah, I see. So that's...
we just change contractible to homotopy S1 and state it as a new theorem.
I see. Now I see.
Or maybe I should here also mention that the not the homotopy S1 piece, but the other one is like you know, the contractible compact pairs, exotic Stein pairs, also constructed by Haydn. Maybe I should just write here. Thomas Mark and Lisa Petrola. And the second corollary of that is there is a homology tree sphere This is indeed our boundary in the above construction. And two knots, let's say K1 and K2 in this homology sphere. And there are indeed here the linking circles of attaching sphere of two handles. To correspond, I mean, if you're attaching like, if you're attaching your two handle, which you draw a knot as an attaching circle, when I call linking circle, I'm really talking about that piece. So those are these, such that zero surgery to K1 and K2 gives S1 times S2, and K1 and K2 are not equivalent. Equivalent means like a little bit different than S3. I mean S3. In S3, if two knots are equivalent, means here not equivalent means there is no diffeomorphism taking K1 to K2. I mean, being equivalent in S3 is being isotopic actually, but in general, tree manifolds is not the case. So we, instead of isotopy, we call equivalence. This is known as a property R in S3, right? So it is true normally if you're in S3, if you have a knot, if you do some zero surgery and get an S1 cross S2, the property R tells you that knot has to be the unknot. And that is to saying, I mean, that was a question in Trovy's problem list that brought our attention after that we posted our paper. And yeah, this naturally solved that problem too. So is this true for the homology spheres? It's not true. There are such examples. And this follows from, I mean, the one like direct, the second follows from our examples. Admits handle body with unique 1-2 pair. So both those manifolds are really can be constructed using unique one handle and unique two handle. So if there's an interest at the end of the talk, maybe we can talk about proof, and maybe, I mean, we should say a little bit more. This is not that obvious if you haven't thought about that question before, and if you are not familiar with the handle bodies. But it's trivial to people who already have some understanding in the question. Okay, so those are the two corollaries. And maybe I can talk about now construction of that kind of, there's a cleaning going on outside. Sorry for the noise. I really want to talk about now the construction.
So sorry, what is the question? It's not a question.
Is there a question?
No. I thought you were asking a question.
No,
so
there were noise that there is a cleaning going on outside of the apartment. So I just said I'm sorry if it's like.
No, I can't hear any noise.
Okay, okay.
So we can hear.
I hear a lot. So I was talking about. Okay, so how we construct this these exotic manifolds, and how do we keep that Stein property? So, I mean, that is the really main part of the most important part of our construction. But before I do that, I need to say like a tiny bit about the concordances, because it has a lot to do with the concordances. So some concordances. We say that is there any questions so far? Am I going too fast or?
For me, it's fine.
So definition, we say two knots in random tree manifold are concordant if there is a smooth, actually has to be proper embedding of an analysis into entry cross I bounded by knots. So, you know what I'm talking about. So if you are in some tree manifold cross I, and if you pick a knot here on the boundary in entry, like there are two knots, right? So if you can find such a concordance, I mean such an embedding analysis, smooth embedding between them, then you call them as a concordant. This is entry cross I. And the theorem if K is really homotopic to S1 cross point in S1 cross S2, so then K is smoothly concordant in S1 times S2. So that's one of the main ingredients. So is there a question? No.
Why it is not obvious? Because it seems that if you just look at the, the homotopy path inside this, term times I. I mean, why it's not obvious? Why you cannot just trace, the path of this homotopy, and that gives you a torus?
Trace the homotopy?
Yeah, you just look at the homotopy of your node, and that gives you an annulus. So why this theorem is not obvious? So what is wrong with the following proof that you just take?
I try to understand your proof. So you have some F, right? You're saying that you have an F from.
Yes. So we just.
Okay, Ft you're saying, like yes. F0 is K, F1 is S1 cross point, right? And you're saying that look at this Ft in this piece, but then you have many like sub-intersections, many double points, right?
I mean, I see. So
like homotopy is just a continuous map. It can be very crazy, and you can make this homotopy like, okay, you can make it immersion. That's also true. You can make that immersion clean immersion. That's also true. And it's also true that if you allow to change that, that's what you do, like crossings, right? Then you go from one to another one. That's perfect. But then you have to get rid of this really like crossing changes in a smooth way.
I see. Okay.
Almost, yeah. This is the idea, but we have to really. We're gonna do this exactly, but we will show that you can get rid of the self-intersection in a smooth way.
Good.
So the proof supposed to be somewhere here. It's here. Thank you, Stein. And it's very easy, Eylem, actually. So, and this proof is really easy. So, okay, as you said that if you have a knot, it's really homotopic to this one. You can go from one to another one by just crossing changes, right? So you agree on that, right? If you're allowed to like self-intersection, you can make it unknot. Okay, so then here is how you can get rid of self-intersections. I mean, how you can get rid of these crossing changes. So I'm going to introduce that crossing change, this piece. So you are at, okay, you start with a knot. I mean, this is how the construction goes, right? I mean, at the top level, and you are moving to the bottom, like you're in S1 cross S2 cross I, and you are looking at the moving pictures. At some level, you are attaching some bands, and you are changing your knot, right? And you are changing your surface. You are attaching some knot bands. You do the same thing at the top, at the bottom level. If you ended up like bunch of unknots and some knot, you can keep all the unknots with a disk, right? And you ended up with some embedded analysis from the starting knot to the end knot. So what I'm saying, I'm going to attach some bands at some level whenever I want to change a crossing of the knot, and those are your band attachments at some T level. Okay, you're attaching bands here, but attaching bands are like nothing. It just changes the crossing on the boundary knot, and if you ended up like the same knot, only one crossing change, but you gain extra one linking circle, right? It's clear from that picture. So that is the whole idea, changing a crossing as a price. You gain linking circle. Okay, so what I'm saying here, whatever the knot you start with, do all these necessary crossing changes, and you ended up with, at the end, you ended up, since you are homotopic to S1 cross point, right? You ended up with that S1 cross point, the knot, which I represent here by K prime, and bunch of like linking circles. But this linking circles slides, I mean, they bounce in S1 cross S2 by this like light bulb trick. When I say I'm sliding here, you remember that I'm doing this one. So you have this S2 here, and you have that bunch of linking circles, and you can slide that linking circle over that S2, and you can see you can see it is really unknot, and you can really make it disjoint. Because I mean, linking doesn't make sense in S1 plus S2, right? So that's maybe another proof to say that, or an example. Okay, so when I'm talking about this slide, I'm really doing this. So then kept them all. So you construct it, it's done. So you literally, what you did, you start the knot and you attach some bands. You ended up with like a bunch of unknots and S1 plus point. Whatever the knot you start with, homotopy to S1 plus point. So perfect, that's the proof. And now we can talk about really the construction quickly. I think I can take all my 1 hour, right? So the construction is going to be not more than 10 minutes. So let's go. And one example to this, actually, I'm going to use in that construction. Maybe I should be really stating here. Where is that? It is missing. So it's that one. In particular, in our construction, we will be using this particular knot K, which is, as you can easily see that if you allow this, if you allow this like self-crossing, it's homotopic to S1 plus point, right? I just pick some knot in this class, then I'm going to use this knot in our construction. So the construction goes like that. Step 1. Start with Stein handle body with some boundary diffeomorphism that doesn't extend inside as a diffeomorphism, but extends as homeomorphism. This is your initial start. So and you can start with Koch in the constructible case. You can start with anti-Koch with the homotopy S1 case. Because whatever I do after that point, I'm not going to change the like homeomorphism type. I'm just going to change the diffeomorphism type. So, and our starting manifold is here. In particular, there is my fork. My fork is. I'm just going to give the one. Okay. So that is to say, you can really start with this fork. It satisfies the properties, and the F here represents the really bounded diffeomorphism, which doesn't extend inside. Okay, and step 2, I'm going to call this here step 2. Construct a homology cobordism on the boundary of W4. That is something I'm saying here. So if this is your W4, I'm interested in constructing a homology cobordism. If this is your M, which is boundary of W4, this is your homology cobordism. Let's call it with H. Okay, so the claim is this particular homology cobordism has some nice properties that makes this two form manifold absolutely exotic copies of each other. If you glue this piece by identity, this piece by this particular F. That looks magical right now, but it's going to be clear soon because H is something very nice. Let's say this manifold is 3-1, this manifold is 3-2, and those are not diffeomorphic anymore. And more holds Stein. So the problem was here actually, okay, you can start with Stein, but once you like construct this cobordism on the boundary, and you're literally changing the boundary here, you're changing the form manifold. I mean, it's still in the same homotopy type, but you're literally changing like many things here, and it's hard to keep that Stein property because you're playing with the handle bodies. By doing that gluing, you're using some locking techniques, and when you start with the Stein, it's not easy to keep that Stein handle bodies. And why it's the case here, you'll see, but with the properties, let's say. H is an invertible cobordism. Also, this is real boundary. When I say invertible, if you take this H and glue along the N upside down, you can take this as a definition, upside down, it becomes really M cross I. I mean, it becomes diffeomorphic to, of course, I should say, diffeomorphic to M cross I. And this diffeomorphism in particular is real boundary. This is a very important piece in the proof. And also, the top manifold, top three manifold, H self-diffeomorphism. Of this top three manifold, top piece of this cobordism extends over H. And this extension has a nice property. It always becomes isotopy to identity over M. So that really gives the proof. I mean, if you believe that we can construct such a thing, at least it tells you they are not diffeomorphic to each other, but then you have to deal with why it is Stein still. So why I'm saying it is enough, because think about those two manifolds are diffeomorphic, right? Whatever this induced diffeomorphism on the boundary, you can just turn upside down your cobordisms and glue it back by this diffeomorphism, and this extends over the upper H. And then after that, these new pieces become M cross I, and it doesn't touch the boundary pieces. That means you are identity at the top, you are F at the bottom, and you have the W4s down. That contradicts with the F doesn't extend as a diffeomorphism. So those two pieces are like crucial parts. So you want this diffeomorphism real boundary, and you want this every diffeomorphism of entry extends over H, which is identity on the top. So
could you repeat again? What is the contradiction?
Contradiction is, I know that F doesn't extend inside.
I see. Mm-hmm.
So what I'm saying here, if you have that this piece here, you glue another piece of H. So normally, whatever that diffeomorphism, if you believe they are diffeomorphic, this is glued by F, this is glued by identity, this is H, This is H. This is H bar. This is H bar. So if just don't think about the H bar parts right now. If those two manifolds are diffeomorphic to each other, whatever it induces on this piece, it extends over here, which is identity also. And also by the properties of H, this piece is M cross I, diffeomorphic to M cross I real boundary. And that is saying that you have like two pieces of W4. You attach a color here by identity, and you attach a color here. Oops, this is being too that going. So that is saying you have here M cross I, you have here M cross I. You're attaching this with F, with identity, and your claim is this identity extends as a diffeomorphism, but this contradicts with F extends as a like diffeomorphism. That is a contradiction. And then maybe in the later last 1-2 minutes, I'm gonna tell you how do we construct M. M is here really. I'm sorry, H. H is here really. You start with M cross I, the boundary tree manifold. You remove some nut cross I and the neighborhood, some like product concordance in the manifold cross I. You remove some product and you glue something S1 cross S2 cross I, some complement, some concordance complement. And here F is an invertible, of course you glue over T2 plus I. F is an invertible concordance from, of course here it is real boundary again, because if you don't start with that one, the cobordism, I mean, this is the way how we get invertible cobordism. So this has to be invertible concordance, real boundary. And I haven't written down as a theorem, but all the concordances that we construct in this theorem are invertible actually. So if you take one concordance and do upside down, it becomes diffeomorphic to product concordance. So it is an invertible concordance from S1 to some K. And this is the picture. You remove this piece, the product concordance, and on the right-hand side, you remove the this interesting concordance, and you glue this complement into the here. Actually, you fill this piece by the complement of the right-hand side. And you do in a way that the meridian goes to meridian, we say. It corresponds to no surgery at the bottom, but it corresponds to some surgery at the top. I mean, at the bottom, you're removing a tubular neighborhood of knot, and you are gluing like S1 cross point complement in S1 cross S2, which is a solid torus. It's like you can think as an unknot in S3. So you glue this unknot complement, or like trivial S1 cross S2, S1 cross D2. So it corresponds to no surgery. So that's why it is starting from M to some N, because it corresponds to some surgery at the top. Okay, and after you do that, you have this H, but you want that maybe there are some other things that you have to be really careful to I mean, this piece gives you invertibility, but also we want this every subdifeomorphism of n extends over the H, and that follows from these two properties. This eta is eta and k both hyperbolic knots. With trivial symmetry. And to keep the sign property, you want that K has high Thurston-Banach number. And indeed, the knot K that I just introduced you about, that I told you I'm going to use, it's this knot. If I put in a like legendary position, the TB is 4 here, high enough for us to keep this sign property. So that is our cork we start with, and last two picture. I mean, you see the cork here, right? The aqueous cork I just introduced you, and you see the knot eta inside. And after this boundary diffeomorphism, you see the image of this knot wherever it goes. So, and the last piece maybe is just gluing those. I mean, after you remove this piece and glue it in the other complement. So we use here the roping techniques that I didn't talk about, but you really ended up with this picture. Maybe.
You need one more page.
Yeah, this is the last stage. That's it. So you can easily follow this, like everything in this picture, actually, how we are working. So this is the first piece of our manifold that we start with. This is a knot inside. That is the knot in S1 process too. And I'm taking the complement of this concordance, and complement is that product concordance. And when I glue them together, they are becoming to those pictures. And you can really follow this piece and that piece here. This is a cork. This is your knot eta inside, and this is your knot in S1 process too, and the similar picture, the image of eta, the knot in S1 process too, and the construction. So those are the final constructions of for the constructible case, and I think I'm gonna stop at that point. So there are something still like to tell you about maybe coping, but those are really nice techniques. Should be really read carefully to understand. It's not easy to explain in a couple of minutes. So thank you for your time.
Thank you very much. Let's clap here. I don't know what is a ritual to thank the speaker. Yeah. So questions from the audience in chat or by voice or by writing. So let's wait for questions.
Okay, maybe we can take like 2 minutes break, or
Oh yeah, sure.
to make it sure, like, I mean, people can think about something, maybe they come up with a question, or then we can finish.
Okay, so let's wait for 2 more minutes.
Okay, sure. Maybe I should also mention that one. I wrote here. So normally in the case of existence of such an hyperbolic knot in some three manifolds are given by Pavese and Forte. So that's why I've taken a note here, but I forgot to mention. So but in our case, we really like find that knot, and but in theory, if you maybe I never mentioned in general construction, so I should remove it.
In fact, that was my question. So why do we need some hyperbolicity here?
Yeah, actually, this piece to make you sure that the n, the set diffeomorphisms of n, extends over the concordance. So you split your you're literally like gluing two hyperbolic pieces and over some T2 cross I, and those pieces are, I mean, hyperbolicity somehow helps you to calculate this trivial symmetry, which means that the knot complement has trivial symmetry group. So every subdifeomorphism is isotopic to identity. So you have that property on the left side, you have that property on the right hand side. Think about your own just on the top, like, and use some JSJ decomposition that every piece, you know, has to go to itself. The hyperbolic piece goes to hyperbolic piece, and you know, each piece has like a trivial symmetry group. So subdifeomorphisms are isotopic to identity, and then you want to extend this over the whole stuff and make it maybe start from here to up and make it identity on the top. So the hyperbolic part used in two places. First, into the like JSJ decomposition while looking at the subdifeomorphism, and the second trivial symmetry. It calculates the trivial symmetry, which is also used to prove so every subdifeomorphism of n extends inside.
Okay, also a question, you promised us to tell more about some corollary number 2.
Oh yeah. Okay.
You can tell a few words probably, not too many, because it's
so
difficult.
actually it wouldn't take more than a couple of words.
Okay, so
what I'm saying here, if you have only one handle, maybe tiny pictures somewhere on the corner will sort it out. So if you have only one handle and one two handle, okay, it can be complicated, whatever. I'm saying these knots are, you have another copy here, right? Exotic manifolds, those are exotic copies of each other. So I'm saying if you take this linking circle here and this another linking circle here, and if you do zero surgery to those knots, I mean, if you do boundary diffeomorphism, they will just cancel out. I mean, zero dot, I mean, you can, in four-dimensional picture, you can think that, I mean, oops. So do you believe that this is the case? Whenever you have like one handle, two handle, if the attaching circle of the two handle goes once in the okay, and so what I'm saying here, so if you just ended up with the canceling pair, so this is your canceling pair. So you can change to this, that this is zero, those two just cancel each other, and you ended up with this manifold. So this manifold is S1 cross S2. So you can do the same thing on the right-hand side. You just take this linking circle, do zero surgery, and do some boundary diffeomorphisms, like just do like handle body calculations. Then you see this piece is also S1 cross S2. But then you want to say that there is no diffeomorphism taking this piece, this knot to that knot. If there was such a diffeomorphism, then you will be carving those diffeomorphisms. I mean, you will be, okay, there's a diffeomorphism from here to here, taking this knot to that knot. Then those two knots bound some obvious disks in this four manifolds. So what I'm saying, you can carve that disks. Carving means really you are putting a dot here and putting another dot here. After you carve, you ended up with, I mean, this diffeomorphism, after you remove something, induce some diffeomorphism on the remaining part. The remaining part is really S1 cross S2 on the boundary, and every diffeomorphism of S1 cross S2 extends inside S1 cross V3. So you ended up with like those two manifolds that you start with are diffeomorphic to each other, but they are asymptotic to each other. So that there are such arguments here.
Okay, I see. Thank you.
Sure.
So more questions. So if there are no questions, then thank you again.
Sure.
I think we just had the first topology seminar online. So we had some seminar online before, which I participate in, but I think that's the first topology seminar in St. Petersburg, which was online.
That's a
Thank you very much.
Thank you so much, Nikita, for the invitation. It was great to be here.
Thank you.
Thank you for everybody who came here. So if you know somebody else who wants to give such a beautiful talk as Eylem,
Sure.
then you can recommend them to come to our seminar, I think.
Okay, so.
Okay, thank you. Thank you.
Yeah,
Then
I'm leaving. Bye-bye.
Then I end the meeting. Okay.